Welcome to Online Precalculus. This is section 3.3, Properties of Logarithms. Our objectives for this section are to use the three basic properties of logarithms, the product rule, the quotient rule, and the power rule, and then using them to expand and condense logarithmic expressions. Then we'll finish up with the change of base property. So because of the nature of logarithms, that the answers to logarithms are exponents, the properties of exponents correspond to properties of logarithms. So for example, when you have two things with the same base, you add the exponents together. So this property, when you combine it with the idea that a logarithm is an exponent, gives you the power rule. And it says that if you have two things inside of a logarithm multiplied together, you can separate it into two separate logarithms. The product is the sum of logarithms. And we can use the product rule to write one logarithm as the sum of two logarithms by expanding the logarithmic expression. Okay, we're going to see how we can pull logarithmic expressions apart and make more than one piece. Okay, just like we have the natural log of 7 times x, this turns into the natural log of 7 plus the natural log of x. We're able to pull this into two separate logarithms. Okay, so let's give this a shot. Important thing to remember is that when we're pulling logarithms apart, they're always going to have the same base. So this is the log base 4 of 7 plus the log base 4 of 5. And again, I use a plus because of the fact that we are multiplying two things inside the logarithm together. Here, and then there's nothing I can do with this, right? So log base 4 of 7, that doesn't really simplify. Log base 4 of 5, that doesn't really simplify either. As opposed to part B, when we split this into two logarithms, we have the log of 10 plus the log of x. Now the log of 10 simplifies to 1. So with this property, I was able to make this expression a little simpler, a little more easy to interact with. Okay. So two more, same idea. The first one is the log base 6 of 7 plus the log base 6 of 11. Two things inside the logarithm can be separated with the sum of two logarithms. And nothing to simplify in the first one, as opposed to the second part B here, separates into the log of 100 plus the log of x, and the log of 100 is 2. So again, I'm able to simplify after expanding. Okay? So the quotient rule comes from the same idea that because logarithms are exponents, we can use properties of exponents to pull these logarithms apart. We'll put them together later. But when you divide with the same base, you usually subtract exponents. Therefore, in the quotient rule, when we have the logarithm of a quotient, it's separated into the difference of two logarithms. What does that look like? So when we use the quotient rule to write a single log, when we use it to make a single logarithm, the difference of two logarithms, again, we are expanding the logarithm. Okay, so if we want to expand x over 2, log of x over 2, it separates into the log of x minus the log of 2, the difference of these two. And again, this is a technique for expanding logarithmic expressions. So let's do the same thing. And again, once we separate them, we can see if we can simplify anything. So the log base 7 of 19 minus, because the x is in the denominator, negative exponents go to the denominator of a fraction. So anything that's in the denominator is going to be a negative exponent. So that's going to be the log base 7 of x. Nothing to simplify there. 7 and 19 don't really go together. So we can go to part B. Whereas here, the log, natural log of e to the third power minus the natural log of 7. Now, I can evaluate the natural log of e to the third. We can use a different property that we'll talk about in a second called the power property to help us, but the natural log of e to the third is asking me if I raise e to the third power, if I have a base of e, what power do I need to raise it to get e to the third power? So this is going to be a 3. Okay? And that does simplify a little bit after we have expanded it. Okay, so again, use the quotient rule to expand each of these two expressions. For the first one, we get the log base 8 of 23 minus the log base 8 of x. Nothing to do with that because 8 and 23, nothing there. So to expand the second one, we now have the natural log of e to the 5th power minus the natural log of 11. Natural log of e to the 5th power is 5. So there's one more rule that we can use to expand logarithms. Okay? And when you have an exponential expression that's raised to a power to a power, you multiply the exponents together. And so this property suggests that we have this property called the power rule. And the power rule is probably the one that we are going to use the most in later sections when we are solving exponential equations. So notice what's happening here. When we have positive real numbers, right, with b not equal to 1, right, bases aren't equal to 1, and p is any real number, what's happening is we're taking this p and we're pulling it to the front, right? Because this is a product, right? This is a power to a power. The logarithms are exponents. It is an exponent to another exponent power. We can multiply those two things together. So the logarithm of a number with an exponent is the product of the exponent and the log of that number. Okay, so you can use this to pull the exponent to the front. And again, this is how we expand a logarithm. Okay, so what we do is we take the 2, we bring it to the front, we get 2 natural log x. Problem though, when we look at the graph of the natural log of x squared and 2 natural log x, they are not the same. So when we look at the natural log of x squared and 2 natural log x, we can see that because we have x squared inside the logarithm, we can't take the logarithm of negative numbers, but if we plug, say, a -1 or a -2 into x squared, it's going to turn positive. And that does not happen with 2 natural log x. You can see that their branches on the right are the same. However, the domain of the natural log of x squared is twice, right? It has a branch on the left, whereas the 2 natural log x does not, okay? This is something that can happen. However, for the focus of this section and in the next couple sections, we are going to assume that all the variables represent positive numbers, so that way we don't really have to worry about the domain of the functions changing when we pull exponents to the front. But just realize that it is a possibility and could happen. Okay? So let's use our power rule to expand these expressions. We're going to pull the exponents to the front and see what we can do with them. So this turns into 4 log base 5 of 7. The 4 jumps to the front. And nothing I can do with that. 5 and 7 don't really work out too well, so nothing to do here. In part B, we have a square root. Remember that square roots can be rewritten as fractional exponents. And now that fractional exponent can be pulled to the front using the power rule. Okay? So that is now simplified. You might also see some, you can see it written like that with the natural log of x over 2. as long as it's not like this in parentheses. The only thing that is still inside the logarithm is the x, not the 2. Okay, and then for this one, right, when we pull this, right, because both the 4 and the x are both raised to the 5th power, okay, we can pull the 5 all the way to the front. Now, there is more that we can do with part C, okay, but we'll get to that in a second, okay? But realize there is another part to this that we can keep going. We could expand it more. Right now, we're just using the power rule, though, okay? So for this one, we pull the 9 to the front, and it's the log base 6 of 3. Remember that the third root means x to the 1/3 power, so that comes to the front, and the 2 comes to the front, and the x plus 4 still stays in parentheses because they are both inside the logarithm. Okay? So sometimes it might be necessary to use more than one property when you expand logarithmic expressions. Okay, so here are my 3 rules: the product rule, the quotient rule, and the power rule. Again, if your question is to expand the logarithm as much as possible, that's really what you want to do. You want to expand it until you cannot expand it anymore. Okay? So here are some errors that you could make when you are using properties of logarithms to expand the logarithm. First, which is shown in the graph in the bottom, these two are not the same. This is the natural log of x plus 3. You can only separate it with addition when it is multiplied. And you can clearly see from the picture that the two graphs are not the same. Some other, and that's this first one right here, that's not correct, right? It needs to be multiplication inside. This needs to be division in order to separate with subtraction. This is multiplication, this should be a plus. This is division. You don't separate it with 2 logarithms, and again, the 2 logarithms don't separate like this. Sort of this one goes with this one, right? This is the correct way to separate a logarithm with division with using subtraction. The last one is probably the most common mistake. Notice that the p is only raised to the n power, and so if you put it in the front here, it implies that you're raising both of those to the p power, which is not what is happening. Okay, so let's expand some of these as much as possible. Okay, so the first thing that you're going to do is separate them with, in this case, addition, and in part B, subtraction. So my first step is to log base b of x squared plus the log base b. I could leave it as the square root of y, but I'm just going to change it to y to the 1/2. Now I use the power rule, log base b of x plus 1/2 log base b of y. Now that is expanded as much as possible. Okay. Next one, we first separate it with subtraction, and you got to be careful here. Let's put this as a fraction. You got to be careful here because we are subtracting the log base 6 of 36, and it's also a y to the 4th, but that's 2 separate terms. Okay, and the common mistake would be like, oh, well, okay, 36 and y to the 4th, they're multiplied together, so you should put a plus, but that's not true. Okay, if you want to, you can put a plus, but only if you put both of them in parentheses, meaning they are both in the denominator, so they are both negative exponents. So you either separate them, either make them both a negative, or put parentheses around the two that are the product in the denominator. Okay. Then we can pull the exponent to the front, log base 6 of x, minus the log base 6 of 36 is 2. And then pull the 4, right? The 4 can come to the front and give me a minus 4, right, as I distribute the negative log base 6 of y. Okay. Let's do these two. Okay. And so we get the log base b of x to the 4th plus the log base b. The bases never change when you're expanding logarithms of y to the 1/3. And then we pull the exponents to the front for log base 6 of x plus 1/3 log base b of y. Okay. For part b, log base 5 of x to the 1/2 minus the log base 5 of 25, and also minus, because it is in the denominator and I don't want to use parentheses, log base 5 of y to the 3rd. The 1/2 comes to the front, minus 2, because the log base 5 of 25 is 2, and the 3 comes to the front, log base 5 of y. So before we go forward, let's go back to this page where we said that there was more you could do to expand this. And hopefully we see this now, because we can expand this to log base 4 plus, and the 5 still goes with the log base 10 of x, okay? Then the common log of x, because both of them were raised to the 5th power. In fact, if we had done this step first, we could have changed this to log base 4 to the 5th times x to the 5th inside the parentheses if we had wanted to. And then you could clearly see that the 5 goes to both of them. Okay. So that is expanding logarithmic expressions, pulling them apart. There's also, if we go backwards, a way to condense logarithmic expressions. And that is writing the sum or difference of two or more logarithms as a single logarithmic expression. And you use all the same properties, the product rule, the quotient rule, the power rule. You just go use them backwards. So if you see a sum, it turns into a product inside the logarithm. A difference turns into a quotient, and things can go, the exponent can be raised inside the logarithm by turning it, the product can be raised inside the logarithm by turning it to an exponent. So let's combine these two terms, neither one of which is easy to simplify. Yeah, 4 and 2, that's a square root, but I'm not sure exactly how to get 32. But what we can do is we can turn this into the log base 4 of 2 times 32, which is 2 times 32 is 64, and the log base 4 of 64 is 3. So because we were able to combine these logarithms together, they became much easier to simplify. For part B, I see division, so this gives me the log of 4x minus 3 over x. And nothing really to simplify there, nothing to cancel. So that one's finished. Log of 25 times 4 would be 100, which would give me 2. And part B, same as the original question, 7x plus 6 over the x. And then nothing to simplify with that expression. Now, important that you remember that the coefficients of logarithms must be 1 before you can condense them using product and quotient rules. So if you have two logarithms like this, the coefficient of the first term must be a 1. So you have to use the power rule as your first step. Pull this exponent back inside to give you the natural log of x squared, and then you can multiply the two expressions together. So that means my first step with these expressions to combine them into a single logarithm is to make this the log of x to the 1/2 power plus the log of x minus 1 to the 4th. And then when I combine them, I can just combine this. I can leave this as a square root if I wanted to, x minus 1 all to the 4th. I really don't want to expand that anymore. I could expand x minus 1 to the 4th power. That would be a lot of extra work. We could just leave it like this. For part B, we get that it turns into the natural log of x plus 7 to the 3rd power minus the natural log of x. And then to combine it into one logarithm, it turns into x plus 7 to the 3rd power over x. When you're done condensing, you should only have one logarithm, right? You should only use the word logarithm one time. For part C, we get log base b of x to the 4th. The 4 comes inside. The 2 comes inside minus the log base b of 6 squared. I could write it as 6 squared. I could just write 36 though, just as easily. Minus the log base b of y to the 1/2, which is the square root of y. Okay, and now I put these together. Both of these two terms are going to go in the denominator because they're both subtracted. So this is x to the 4th over 36 square root of y. I would leave it like that as opposed to trying to do something like rationalize the denominator and go crazy with other algebraic techniques. All right, you can just leave it as the combined logarithm. Okay. Let's try 3 more. So for part A, we have first step, natural log of x squared plus the natural log of the 3rd root of x plus 5. And then combining them gives me, with multiplication, x squared 3rd root x plus 5. Part B, the 2 goes to the front, or the 2 in the front goes to the exponent. So that would be the log of x minus 3 squared minus the log of x. Combining those with division over x. And then finally for part C, the 1/4 in there, let's just write that as a root. So that's the log base b, 4th root of x, the 2, minus the log base b, 5 squared, again, can change that to a number, 25, and then minus the log base b of y to the 10th power. Combining these into one logarithm, all with the base of b, gives me the 4th root of x over 25y to the 10th. Again, both of these terms go in the denominator because they're both negative exponents. So the last thing in this section is something called the change of base property. So some calculators have a button that lets you kind of do any logarithm you want, or have some sort of math function that'll let you do any logarithm base you want. Some calculators don't have that. So if your calculator does not have a logarithm a button that'll let you do any logarithm, it's probably likely that they can do a common logarithm and a natural logarithm. Okay. So if you have something that's, say, like, the log base 5 of 30, I can't do that in my head. I know it's a little bit more than 2, but I don't know exactly. You're going to need a way to do this. And that's the change of base properties. So for any logarithmic bases, a and b, any positive number m, the logarithm of m with base b is equal to the logarithm of n with any new base. So this number can be anything as long as it's the same. And you just take the inside of the logarithm goes on the top, and the base goes to the bottom. Okay, and again, when you're using the change of base property, it's base b in the original logarithm. It's the a that's the new base, so you can use any base you want. Most calculators, if you're having to do this formula, it's because your calculator doesn't have any base and it only has base 10 or base e, natural logarithms or common logarithms. So if you're going to do this, might as well make the bases what is on your calculator, which gives us the formula in terms of the buttons that you see on your calculator. So the log base b of m with common logarithms would be the log base 10 of m, right? Just log m over log b. And with natural logs, it would be the natural log of m over natural log b. So what this lets you do is it lets you use your calculator to use to calculate any base that you want. Okay, so let's use common logarithms. The log base 5 of 140. So if I change this with common logarithms, log base 10, so that's the log of 140 over the log of 5. And when I do this, I get 3.0704. Okay. Common logarithms for the next one. So the log of 7 of 256, oh, sorry, not 256, 2506 is going to be the log of 2506, the inside over the log of the base. And when we calculate this, we get 4.022, round up, because it's 99. Okay, so this is now, it's possible to use any calculator no matter what. And these are going to be the same thing, same numbers, and you can see that. So the log base 5 of 140 is going to be the natural log of 140 over the natural log of 5. That doesn't mean that the natural log of 140 is going to be the same as the regular log of 140, but this ratio is going to be the same, and this is going to give you the same answer of 3.0704. Okay, try it on your calculator to make sure that you understand how this formula works. And again, if you have a calculator that can use any logarithm, then you don't really need this formula. Okay, that was section 3.3, properties of logarithms.